Hi, my name is David Ryan. I'm a graduate student at the University of Arizona in Applied Mathematics, and today I'll be going over a literature review and the mathematics of drones, control path planning, and coordination. How does this relate to EUEC? Is that this can be used for power plants and using large language models on the drone to investigate sensors and other things, and then the feedback from those sensors to then inspect other parts of the power plant. That's not the main focus. That is a possible use of this mathematics, but it's going to be I kept the theorems out of it. I'm mostly going to be providing results, so it's just math warning here. And but pretty much, I'm going to talk about briefly talk about the applications, and then get into the meat of the mathematics. This is just a way of giving me experience for presenting, and thank you for your time. Thank you. All right, and my advisor is Professor Haseen Rasgaftar in the Mechanical and Aerospace Engineering Department. He's part of the Applied Mathematics faculty, or will be shortly. So, all right. So the motivation is part of the economic compound annual growth rate of 27% for UAVs between 2022 and 2030 by Spherical Insights, an investment strategy website. And drones are ubiquitous. We have commercial, military, and security applications. In UPS in 2019 received standard certification, which allowed them to fly drones beyond visual range. That brought about new issues with robustness to obstacle avoidance. We also have military applications. State estimates of a military aircraft is essential for guiding munitions to the proper target, and then also for Border Patrol. For incursions into the United States, we're able to maximize coverage and find a way of maximizing coverage for a given flight time. So that's so just some examples. But now some interesting problems that arise from these applications. So one thing is that we want our drone to be robust to collision with moving and stationary objects. We want autonomous operation with as few inputs from the user as possible. So we want it to act on its own without much guidance from a ground station or a human input. We also want to control by minimizing states, inputs, and noise and uncertainty to improve the performance of our system. Another thing that we're going to be interested in is how to best coordinate mini drones in terms of path planning and control. So, for example, what is the best route between A and B, and how are we going to what control inputs are going to be necessary to achieve that? And so, pretty much, also want to explore other mathematical machinery not already in use or generalize existing methods, which I'm currently learning in the applied mathematics curriculum. So the paper investigated is integration of A-star algorithm searching classical optimal control for safe planning continuum deformation of a multi-quadcopter system. That's a mouthful. By Haseen Rasgaftar of the as I mentioned before, and we're going to investigate that paper, and then afterward I'm going to provide my contribution. So the first part's going to be cited for his paper, and then the subsequent part's going to be what I did last semester to contribute. And there's a little bit of add-ons because I am taking a course in optimal control, so there's a little bit of new information. This is sort of it's a little bit of a recycled presentation, but thank you for bearing with me. So continuum deformation of so important points of the paper is that if you have a swarm or if you have coordinated drones, like in leader formation or leader follower formation, you can describe that mathematically as a continuum deformation or leader follower formation. So, for example, follow the leader. Every leader drone would have drones that follow its path behind it, and then you have swarms, which means they have a network of drones creating particular objects. I'm sure you've seen drone shows and so forth. A lot of the mechanics that go into to that require continuum deformation. Obstacle avoidance via containment ball and tetrahedral obstacles. So the idea is that you discretize your arena or your region into discrete points in which a sphere can navigate through a course where the obstacles are modeled as tetrahedrons. As far as getting from, and once you discretize the grid, you want to find the quickest path between the optimal path between 2 points, and then we're going to talk about the A-star algorithm, how to navigate to a target with the least navigational cost. And then we're going to talk about optimal control. We're going to talk about what my contribution is going to be with gain scheduling, but we'll briefly talk about optimal control and what Ross Goptar did with that. So continuous transformation. So we have, let's imagine we have 8 different drones here in this, and then we have at a later time we have this configuration. All right, so not much has changed. Maybe it's been displaced by 5 meters. So the idea is that we would have the final position as pi. We would have the rigid body displacement parameterized by a unit vector in the direction between the 2 points. So from point 5 to 5, we would have a line attaching these two, and then it would travel in a rigid body formation from 5 to 5. And Q of t for rigid body formation is the identity matrix, but it can Q of t can also be shear, it could be rotation. So pretty much it describes the motion of this of each one of these nodes, which is a drone, and it's parameterized by time, and it shows the transition from one cumulative state to another. Pretty much we're going to talk about rigid body motion today. So Q is going to be equal to the identity matrix for the most part. So we're going to talk about obstacle avoidance. So quadcopters are contained in a sphere encompassing all drones. Each drone is encompassed by smaller spheres. So the idea is that we have a large sphere that surrounds the formation, and that allows us to dictate global points where this sphere can navigate through these tetrahedral obstacles. Okay? And then the smaller spheres, we can put constraints on the Q of t matrix that we saw from the last slide to restrict the eigenvalues, and with that we can ensure that there is no collisions between the drones with each other, and we can avoid obstacles by making sure we're in the set where we have the rigid body displacement in a ball of R max. So this is the region in which our drones can navigate. Okay, so I won't go too much into the detail, but it involves eigenvalue decomposition and restricting the eigenvalues to inequalities. But path planning. So path planning, we have A star is the path planning algorithm to best navigate a discretized obstacle course. Okay, so let's start with a simple example. So is everyone familiar with the Manhattan directions? So if you're traveling Manhattan, you're going up, down. Oh, you are. I know you are. But you're traveling up, down, left, right, diagonally. So if we start here, and we start from this node and we proceed to each one of these other nodes, and the cost of going to one adjacent node is 1, and the Euclidean distance between this node and this node is square root of 2, and from here to here is 1. So that's the cost of going to an adjacent node. But the heuristic, which we add on as plus h of n, is the Euclidean distance between your current position and the end. And the idea is that you want to minimize this quantity. Okay, so you're going to start here. So it turns out that this particular quantity is about 5.66. So we're going to go here first, And so 5.66 is less than, so you think that this would be the best algorithm. So we can't go to any of these. What's in orange is an obstacle and it has infinite cost. So we can't go to these nodes and minimize the cost. So at this point, we take the minimum of the nodes that we have. We have 3 nodes, and we go to the next position. And we finally exceed what the previous node was. So we then extend this path in blue, and then that blue path is less than the path of going greedy first here. And obviously, this distance is less than this distance. And so then we find that the optimal path is this sort of L shape here. So that is a star algorithm in a nutshell for path planning. So optimal control is we have this. I'm going to call it a cost function, but it's called a Hamiltonian. But I'm not going to go into that. I'm going to talk about we want to minimize a cost such that the state expenditures and the input expenditures are minimized, so we can find a controller and trajectory. So we do that. You would solve what's called the Hamilton Jacobi-Bellman equations, which are nonlinear partial differential equations, which are very hard to solve. And when I wrote this, I didn't know how to solve them, so I had to find another way of doing it. So what I ended up doing, before I go into, I'm going to go into that a little bit more. But before I talk about that, I'm going to say you can also minimize the cost with respect to time. So the idea is that you minimize the time expenditure between 2 points, and you can find a control input that does that. So what I end up doing is I came up with a simple research project that could be done in 10 weeks. And so I came up with one drone with simplified dynamics. So the trajectory, our Q matrix from before was the identity matrix, and the desired trajectory desired trajectory was sorry, I'm having a moment. Was having discrete points along the graph in which the drone would it's desired it would go to, and it would use an A-star algorithm to find the path, define the optimal path between the 2 points. And then the simplified dynamics was using Newton's second law. Okay, now I know. We use Newton's second law with spring damper dynamics, and we minimize the cost function with respect to the states and input piecewise between waypoints with proportional derivative controller, also known as optimized gain schedule. So pretty much we have a state matrix, X, where we have X and Y direction. We have our inputs. We have our proportional derivative control. We have a cost function to be calculated at each waypoint. And we have gradient descent, which updates our damping coefficient, such that we're able to smooth out a path that this drone can follow. Okay. So we have X targets get A-star path. We have the start, end, and obstacles. We have a while loop here where we minimize the norm of the cost function such that it's greater than epsilon, and we wait until this gets minimized or close to 0. And while we're not at that waypoint, we desire to go to that waypoint, and then we sum up a cost function, and then we use a finite difference scheme to find the derivative of the cost function, and we update our KD, our damping term. And so the idea is that we have this annealing effect that we don't explicitly state what the path is that we know the waypoints that the path is going to take. That's the A-star algorithm, but we don't know exactly how it's going to navigate to those points. So what we end up doing is we have this annealing effect when we run this code. So we have this spring mass damper type dynamics, and we're minimizing J at every point, and we find that here's a obstacle, and when we minimize the cost function, we get this annealing effect where the red line converges to the optimal path between 2 points. Okay. We incorporate, so future work, incorporate optical control and obstacle avoidance guarantees with multiple drones and continuum deformation as part of an optimized gain description control problem. But I'm also learning right now in class about the Hamilton-Jacobi-Belmont equations, and establish horizon of path planning to account for moving obstacles in an environment for concurrent path planning and optimal control. Account for uncertainty in states by implementing Kalman filters and adding noise to measurements. And I will have a much better presentation next time when I take a course in optimal control my second year. So thank you so much for your patience and your kindness. I appreciate it. Thank you. Any questions I can answer?
You just threw out words that make you flash back to college account
Yeah.
and different equations and everything else. So.
Yeah, it's well, thank you for your patience. I appreciate the experience. So what we're doing right now is we're using a large language model with a drone with ChatGPT that's able to investigate U of A's signs like banner health and to request to ChatGPT what that is and to pretty much interrogate its environment. So we're doing that right now with another professor, Merrick and Jack Robbins, and so we're working with that group as well, and the future's great. So thank you so much. I really appreciate your time.